Hello everyone. So in this video we'll be discussing about the memory organization in a logic circuit. So basically a, a memory means it's a storage device. Okay. As far as the digital circuit's been considered, this flip-flop forms a basic element of an memory. Okay. So a group of flip-flops combined together to form a word, and many such words are cascaded, and it is provided as a bank of memory. So before getting into that, then how the memory is referred and how it is being observed. Okay, so it is purely dependent on the addressing, how a memory is organized and how the data is stored in it. It's purely dependent on how the memory is organized and how it is being addressed. Okay, suppose let us take an example. If we want to address one particular memory location, so I need to create one unique ID for it. Okay, so in the digital we'll be representing in terms of bits. So a bit can be either 0 or 1. It may have two unique values. If I have two bits together, I can generate four possible combination or four possible unique addresses with two bits. Okay. If I have three bits, I can generate 8 different unique locations or unique addresses with 3-bit combination of the binary values. So if we take an memory, how the sizing is fixed is based on the address bus. Okay, the width of the address is going to specify the number of memory location, and how it is related. If n is the number of if k is the number of bits in the address, then we can generate 2 power k possible memory locations with k bits of address input. Okay, so in general how it is being represented is m words cross n bits per word. Memory is referred with like this: m cross n, where m is the number of memory location or the number of words, and n is the number of bits per word. In the word length, nowadays we have minimum 8 bit as the data size. It can be 8 bit or 16 bit or 4 bit or whatever it is. So depending on the how the memory is organized. So before entering into the memory organization, let us discuss about how the structure of a memory cell will be. Okay, so a single cell represents a flip-flop which is capable of storing 1 bit of data. Either it can be 0 or 1. Now when it comes to the flip-flop, or when it comes to the memory, what are the basic operations we can perform as? Either we can read data from the memory or we can write data into the memory. So in order to perform the data read or write operation, the particular memory cell or the particular memory location must be selected. So apart from the input and output, we need three different control signals. One is select, means selecting a particular memory location, and then read or write command. So these are the three command inputs we need along with the input and the output of a memory. So this is a structure of an SR flip-flop based memory cell, which is having one input and one output and two control inputs, select and read bar write. We see the if you observe this read or write command, at a time we can perform any one operation only. Either we can read the data from the memory or we can write the data into the memory. So this control signal is combined and it was provided with different logic. If I want to read, then I should keep the logic to be set as at this input to be equal to 1, or if I want to write data into the memory, I should set this value as 0. So with a single channel I can implement two different functionalities, and this is called the multiplexing of the function. So what is the result of this is I can reduce one number of pin. Suppose if the read and write signals are not combined, then what I need to do is I need to have a separate input for read and a separate input for write. But now in the single channel is being used to perform both read and write operation. So let us see how the data is organized and how the memory is selected and how the data is read or written into the um, memory cell. So just first let us consider I want to read data from this cell. So first of all, what I need to do, I need to select this memory cell if I want to read data from it. So I should keep my select signal to be equal to logic 1. If this is equal to logic 1, then if you see this, these two AND gates will be enabled and these two AND gates will be enabled. Now let us see this. I want to read the data. So if you want to read the data, then I should provide logic 1 over here. If this is logic 1, then here it is 0. So means these two AND gates are disabled. Why? Because irrespective of the other inputs, one input is 0. So the output of these two logic AND gates will be 0. Means applying 0 0 to the SR input. If in the case of SR flip-flop, if the inputs are 0 0, no change condition will be there. Means that whatever the data stored in the previously, the data will not be altered, it will be retained as such. Now if it comes to the output AND gate, in the output AND gate, select already it is enabled to be 1, read it is enabled to be equal to 1. So whatever is the third input will be the output. Means whatever the Q output, the data stored in the memory is available at the output. So this is the condition for read operation. If I want to perform write operation, then I should keep large, again the select signal remains 1 and this reads bar write signal should be given logic 0. Once this is logic 0, this output AND gate is disabled. Means whatever the changes are will never be reflected here. It will produce an 0 output. And if you see at this inverter, this is equal to 1. Now if I take these two AND gates which receives both the select input and the read bar write input, both are equal to 1. And if I see here to one AND gate input is being directly applied and to the other AND gate the input is complemented. So what is the benefit of this? This is resembling similar to that of a structure of a D flip-flop. So what is the condition of D flip-flop and how it has been derived from RS? If S and R are given or complement to each other, then it will act as a D flip-flop. So whatever the input I present at the input, either if it is 1, 1 is stored. If it is 0, 0 is stored. So if you ignore this and these two AND gates, this SR flip-flop along with this input and this NOT gate will perform like a D flip-flop. So and here the write function is enabled by this one and the particular memory is selected, memory cell is selected by the select signal. So like this memory cell basically is functioning. So this is the logic diagram of an memory cell, and in the schematic how it is being represented is a binary cell represented by the block diagram representation, which is having an input and output and two control signals. One is the select signal from the top and the read or write signal from the bottom. Okay, and if we want to have in a real memory, many such binary cells are arranged in the form of array. It's grouped in the terms of, in the form of array, and this is one such memory structure. Okay, so here we have an memory of 4 cross 4, means that I can store 4 words with each word comprising of 4 bits. So every binary cell corresponds to 1 bit. So and every row corresponds to 1 word. So this is first word which comprises of 4 binary cells, means 4-bit data. Second row for second word, third row third word, and fourth row for fourth word. How these particular we can observe this, the word select signals and the binary cell structure. If you take it, whatever the control signal we have applying from the top is the select, the particular binary cell select, and from the bottom we are applying either read or write signal. If it is 1, it is read. If it is 0, it is write operation we are going to perform. So you see here, these are the select, these are the read write control signal. This is the input and this is the output. If you see in the row wise, it's a word, In the column wise, it's a particular bit. So if I take it here, this is one bit, second bit, third bit, fourth bit of the output data. And similarly, these are all going to be my input data. Okay. And since it is an 4 memory location, with 4 memory location, we need an address of 2 bits. So you'll be having a 2-bit address lines at the input. So basically, while addressing a memory, what will be present here is we'll have an address inputs applied to an n k cross 2 par k decoder. Okay, so decoder is one of the major element in the memory. Why? Because it is going to decode the address location or the data location. Okay, so once the decoded, for an example, if I keep 00 is my input, then the word 0 will be selected. This particular output will be equal to 1, means the binary cells corresponding to this row are selected, and then according to the read or write signal, either we can write data into the binary cell or we can read data out of the binary cell. And if you see across all the column, all the outputs are combined and it has been applied to the OR gate. So if this particular binary cell is being enabled, then the whatever the data stored in this is available in the OR gate, and the remaining all other values will be equal to 0. And similarly for all the columns present in this. Okay, means that this OR gate will be having 4 inputs, and this OR gate will have 4 inputs, this OR gate will have 4 inputs, and this OR gate will have 4 inputs. So how many inputs then that each OR gate will have? Each OR gate will have uh, the number of inputs equal to the number of words that a memory is capable of storing. Now the hint here is, so decoder plays an integral part of the memory. So now the coming to the design constraint. Okay, so now if you see this, I have a 2-bit address. With the 2-bit address, a decoder is capable of generating 4 product terms using 4 AND gates, and these each 4 AND gates is having 2 inputs. The 2 inputs is nothing but the bit of the address. Okay, so if I want to generalize this, I can take this as an n input decoder is capable of generating 2 power n product terms using 2 power n AND gates, and each AND gate is going to have n inputs. So what is the disadvantage of this is this will increase the number of gates and the number of inputs per gate. So let us consider an example. I want to address an 1 KB memory, 1 kilo byte of memory. Okay, so if for addressing an 1 kilo memory location, that is 1024 memory location, I need a address bit. I need to have an address size of 10 bits. So with the 10 bits, I need 1024. I can address 1024 memory location, means I need 1024 AND gates, and each AND gate should have 10 inputs. Okay, so this is a great drawback when I go for a large scale integrated circuits. So I want to have a chain. So now in this case I wanted to modify how I am going to address the data. So what we are going to do here is, instead of addressing the individual locations in one dimension, see in the previous case what we have done is, if we consider here 4 words are there, 4 words are arranged only along the row wise. So now I am going to, I suppose if it is 1024 1 KB of data, means 1024 memory location, means I'll be having 1024 lines in this way along the rows. I just wanted to have a modification over here. So instead what I'm doing here is I'm going to consider I'm going to take two 5 cross 32 decoder arranged in the form of array. So I'm going to, again the number of address bit required is remains the same for 1024 location, but how it is being organized and address alone is different. So out of 10 bits, what we are going to do here is the MSB 5 bits are taken along X direction and the LSB 5 bits are taken along Y direction. Okay, and with two 5 cross 32 decoders, we need only 64 AND gates, and each AND gate is capable of holding 5 inputs at a time. So if we see when compared to this, the direct of 10 cross 1024 decoder, where we need 1024 AND gates and each AND gates having 10 inputs. Here the number of AND gates required and the number of inputs per AND gates are greatly reduced. So this is one structure where we have this. I have an 5 cross 32 decoder here and 5 cross 32 decoder here. So the X indicates the MSB 5 bits and this Y indicates the LSB 5 bits, and the intersection of every row and column is mentioned as a dot is a particular memory location. So every row I'll be having, in each row I have 32 memory location for all the 32 rows. So totally we have 32 cross 32 1024 memory locations. Suppose if you want to address the memory location of 404, how it has been addressed is the 10 bit equivalent binary equivalent of 404 is derived. So this is the 10 bit equivalent of 404, which is 01100 along X and 10100 along Y. So these 5 bits are placed at the input of this decoder corresponding to the decimal 20, and this data is present in the MSB inputs of the decoder, which is corresponding to 12. So the particular memory location corresponding to 12th row along X direction and 20th column along Y direction indicates 404th memory location which I want to access. So in this way the memory is addressed in the two-dimension mapping. In other words, it is called coincident mapping. Thank you.